then guys, let's kick it off. We have a lot of stuff to get done in the next few minutes. So I'm talking about reactive architectures. First things first, maybe. My name is David Leitner. I'm a coding architect at Square Solutions. Basically, that's a Viennese company. Worked for quite a while in Germany, so mainly worked for big in bank industry for big German Austrian banks, and I'm now back in Vienna, and my job title is coding architect. I like it quite a lot because I do a lot of architecture, but I still try to keep my hands dirty and work together with teams on realizing this architecture, right? So that's enough about me. Everything else you can find on the internet, right? And on Twitter, you see the handle on the right hand side. Yeah. Let's jump into the real interesting part, and the topic is called Rethinking Reactive Architectures. So we first of all need to understand what is reactive, right? We see it everywhere these days in software engineering. We see it in many frameworks. We have Project Reactor. We have React as a very popular web framework. We have reactive extensions and so on and so forth. But what reactivity in a nutshell is that it's based on asynchronous data streams. So we build and design and program upon asynchronous data streams. And that's the most important thing we need to understand. Before we talk about reactive architectures and all the stuff, we need to really understand it's all about asynchronous data streams, right? And I usually have the feeling that, I mean, even if we talk a lot about Kafka and all these technologies, streams are still not clear to everyone, because a stream is a very simple concept actually when it comes to programming. And when it comes to data structures in programming, we usually have two axes, right? We have an axis of space and an axis of time. Sounds super complex, it's super simple, right? But explains what a stream is very well, yeah, for those who are maybe not still so familiar what is it exactly when we talk about streams. And if we're in singular space and in synchronous time, what we usually have, we have a value, right? Each programming language, doesn't matter which one, has a value which supports a getter and a setter to set this value. If we move to plural space but stay in synchronous time, then we kind of usually have collections with an iterator, generator, lists, arrays, however they're called in the programming language. But most of the programming languages come with the default kind of data structure for plural space and synchronous time. When it comes to asynchronous time and singular space, then what we usually have is something we tend to call promises, right? Some program languages like JavaScript directly have support for promises. So the language comes with promises with computable features in Java. So that's usually a concept which more and more programming languages start to adopt. So basically, they come baked in with this data struct for asynchronous time, but singular space, right? And now usually if I have an audience, if I ask him, okay, and what is now on the right-hand side on top, right? So plural space and asynchronous time, right? Well, that's basically a stream, right? And the thing is, streams are still so unfamiliar to many people because most programming languages don't have them out of the box within their programming language, right? And more languages start to adopt. We see streams getting a first-class citizen, so to say, in many programming languages. But usually they were extended, and one popular extension, for example, are reactive extensions, which basically bring streams to nearly all programming languages we have out there, right? And this is where this whole journey started of reactivity, and people realized, hey, programming with streams is cool. But what is then cool on it? Why do we do it, right? And usually I come up with a very super simple example, yeah? And that's the example. Doesn't matter which code it is. Basically, it could be, I guess, variety of programming languages these days. But we have a counter, right? We set it to 1. We have doubled, which is basically a counter multiplied by 2, right? And now the magic is happening, right? We set counter to 3. And the question I usually ask is then, okay, what's the value of double now, right? And then people think for 2 or 3 seconds, usually at max, and then they say, well, the value of double is still 2. And of course, you're right, because if we want to change the value of double, we need to reassign it again with the new set counter. And that's basically the main criticism the reactive community makes on programming languages these days. It says this relationship between double and counter in this specific example is very implicit, but it shouldn't be that implicit. It should be explicit, right? We should have a way to explicitly define, hey, whenever counter changes, this has an impact or should have an impact on doubled, right? And there's this very old blog post from Paul Stovall about reactive programming, and what he usually uses to describe this concept is a destiny operator. And if you take a very clear look on line 2 now, you see that doubled is not an equal sign anymore, but it's kind of a, destiny sign. So doubled is basically the result of counter multiplied by 2. And if we now would set counter to 3, in a reactive world, doubled would be 6. And that's basically it. That's reactive programming in a nutshell. Yeah, didn't want to take too much time from you to explain this, but that's what reactive programming is all about. And what has this to do with streams? Well, usually we implement this with streams, right? Counter would be a stream, double would be a stream projection. So basically we map the counter stream, multiply it by 2, and that's basically an stream operation, which is very simple, taking one stream, multiplying it by 2, having another stream, right? And this usually then results in a result stream, which is then basically 2. And if we now set counter to 3, all we do is we publish to the counter stream a new value, right? And this affects, of course, the projected stream automatically and increases here the value to 6. And if we then assert, everything is fine. And that's how reactive programming is done, right? We work with asynchronous data streams to get exactly the concept of this destiny operator explained before. And that's reality, right? If you're maybe familiar with the Angular framework, right? Angular pushed IXJS very heavily, and they introduced the reactive extension as first-class citizen of the framework. And in IXJS, this would basically look like this, right? We have a behavior subject, which is basically just a stream with an initial value of 1. We have a count, a doubled, which is basically taking the counter stream, multiplying it by 2. And if we then change the value of the counter by emitting a new value, then basically what I showed you before, the assertion is really working, right? And if we take a look at more modern frameworks, you could even say like Svelte, right? They have this baked into their technology. They say if you assign a $sign in front of a value of a variable, then it's basically reactive. So whenever you change counter, double will be affected, right? And that's interesting, because we talk a lot about, or we will talk a lot about reactive architecture, but I think that's important for people to understand, what is this all about? It's all about working with streams, right? And having this kind of projected streams. So that was enough theory. I'm also lecturing at the university, so that's maybe to give you a little bit of background. I usually like to start to explain the concepts on a theoretical level to make it understandable. In a real world example, well, let's think of a super simple example where we have yet another mail service, right? And here we get a new email, right? And in this example, we could, of course, implement this very simply, right? We could say, when you want to reload your emails, you click a reload button. This reload button goes to a controller. This controller has a kind of data set of current emails. Then it goes to kind of a REST client, and this REST client then returns. If there's a new email, we update our data set, and then we update by elements, right? That's how it's usually done, how it was very often done, right? Well, if we would implement this very simple scenario in a reactive way, then first thing, we wouldn't need a reload button, right? Because we would have kind of an event stream. And this event stream would basically, I guess, contain our emails, right? So all the emails we have pile up there, right? And what we basically do is we just subscribe to the stream. So we don't ask it for data anymore. We subscribe to it. So we tell them, hey, whenever something changes, please let me know. And for example, in this counter, we would basically just make a subscription and then kind of a stream transformation. And we would apply count stream transformation. And based on the amount of emails we have, we would see the amount of emails we have on our UI, right? And here on the inbox table, we would basically just make a collect and a map, right? It doesn't matter in detail, right? But in theory, we would just transform this existing stream in a way how we would need it. So we would map, for example, these emails to these wonderful titles. And here we would basically just do a filter whenever the email is new, right? We show it, and then basically we count it again. And for fetching data, we would basically use something which is also supporting this push way of designing, right? So we would not use a REST API, maybe we would use a WebSocket client. And this WebSocket client, whenever a new email is appearing, pushes us this email into our stream. And automatically, we don't need to do anything. Everything gets fascinating updated, right? And that's the idea. So we move from pull-based design to asynchronous push-based design. That's what we basically do when we think of reactive design, when we think of reactive programming, right? And I started now a lot to talk about reactive programming, but basically the title is not about reactive programming, right? It's about reactive architecture. But as I said before, in software engineering, we often see similar concepts on different levels, right? So many concepts which you see on a software design level, you can also apply on an architecture level and vice versa. And that's the same thing for reactive programming. So basically what we do with reactive architecture, right, is we take these concepts and move them to a system architecture level. And that's what we tend to call reactive architectures, right? We hope that this works, of course. And why do we need this? Why do we need all this stuff? I mean, our systems work all fine. We all know this, right? Why should we care about reactive architectures, right? Well, life was easy. Back in 2010, when I did my really first big enterprise projects, we usually use the universal BBC architecture, right? Anyone? It's hard. I cannot see you. But I usually would like to know if anyone knows BBC as well. They were super simple, right? We had box, cylinder. That's what we usually did, right? This is how most of our architectures look like. And this was fine. I don't say that anything was wrong with this, but usually, the world changed since 2010. And even if we think the world has changed a lot since 2010, the internet has even changed more massively, right? Take a look at these numbers. So in 2010, the internet had about 1.4 billion users, right? In 2020, the internet has 4.7 billion users. And Facebook alone has 2.8 billion users. YouTube has 2.1 billion users. And many other big companies have similar numbers. But this means that a single website these days, right, may have as much traffic as the entire internet did a decade ago. And I don't say that everybody needs to think in reactive architectures, but if you work in companies like big banks, like big financial industries, like big insurance companies, maybe like big e-commerce shops, right? All these things, then you will maybe have a total different amount of customers you need to bring value to than 10 years ago. And that's basically why people were sitting together and said, hey, we need to think about this, right? Software architecture needs to change because the requirements, the non-functional requirements on the software architecture changed. And that's why people basically came up with the Reactive Manifesto in 2014 and said, hey, let's come together and think about what is reactive, what's all this about. And if you Google for reactive architecture, you basically find this manifest, right? And people then usually read it, but they don't fully understand it. And latest, if they see this diagram with all these boxes and arrows, everybody's confused, right? But in a nutshell, that's the most important thing you need to understand here. This diagram, if you understand this diagram, in my opinion, you don't need to read the rest, right? So that's why I will quickly explain you what is this all about here when it comes to the Reactive Manifesto. Well, as I mentioned before earlier, software architecture is all about non-functional requirements. We define software architecture based on non-functional requirements mainly, right? This can be latency, this can be consistency, this can be availability, this can be scalability, right? This can be resilience, this can be reactiveness, right? And when it comes to the Reactive Manifesto, we mainly work on the non-functional requirement of responsiveness. So if we want to build a system that's maximal responsive in terms of resilience, in terms of giving a user fast feedback and being available for the user, then the reactive manifest, then the reactive architecture is mainly a good fit in terms of architecture, right? If you don't want to have this at all and you say, hey, oh no, I just build a small application for 50 MB, then obviously, I guess, going into a full-fledged reactive architecture will maybe not be a good fit. But if this non-functional requirement of building a super responsive and high scalable system, then the reactive manifesto is usually a quite interesting thing to look at, right? And that's the first thing of this diagram I showed you before. So if you want to have those non-functional requirements, maybe consider reactive architectures. And why? Well, those people say, if you want to build a system responsive, then you basically need two things to achieve. You need to build it elastic and you need to build it resilient. So elastic basically means we can scale it horizontally, right? We can start new instances instead of scaling up a single instance. And resilience, as I mentioned before, means basically if parts of your systems don't work, the overall system should still work, right? So those two values support us in being responsive. And now the real interesting part comes. These two values can be enabled by a single thing you need to do. And they say the thing you need to do to be elastic and resilient is to be message driven. And if you are message driven, you support all these values are written above. That's the idea. Super simple. We could say just be message driven and you get a responsive system. Of course, we all know in reality it's not that simple, but let's dive a little bit deeper into this. How does message driven help us in being elastic? Well, let's take the simple example of microservice A talking to microservice B, right? Let's assume we have a very high load on microservice A. And then respondingly also, of course, on microservice B. So we could then start to scale out our system, right? Meaning, as I mentioned before, having multiple instances and not scaling up a single instance. That's what you usually do in a distributed system, right? And now you have this problem, microservice A needs to talk to one of those instances of microservice B. And of course, you can work with load balancers, you can work with reverse proxies, all this stuff. But it could be solved easily by just putting a stream, a queue, whatever it is, at this point, not really important, in between. And when microservice A is getting a request, it's not forwarding it directly to one of microservice B's, but it's just sending an event to a stream, right? And whoever is interested in the stream, and this can be 1 or 20 instances, just subscribe to the stream. And they just take it. And the first one who takes it basically owns it and starts to work on it. So we can out of the box basically horizontally scale when we follow this idea of being message driven. Let's talk about resilience. Very simple. Microservice A talking to microservice B. Microservice A gets a request, forwards it to microservice B, right? Microservice B is maybe very slow right now. I don't know, maybe legacy system or bad mood, whatever it is, right? We see this very often that systems suddenly start to react slow and we are not 100% sure why, right? So let's assume here microservice B is slow, high latency involved in this service. Well, this leads to the direct effect that microservice A is also slow, right? Because it's waiting for the response of microservice B. And new requests coming in start to pile up, right? They start to pile up and pile up and pile up and pile up. And at some point in time, obviously the system is not able to respond anymore. But at some point in time, hopefully also microservice B responds, and then we respond back to the whole response up to the user maybe, and then we can take the second request. But of course, that's not optional. That's not optimal. That's usually which brings a lot of headache if you work in high scalable systems, especially with a lot of users. Then you usually don't want to have this bottleneck then spread over your whole system because a single service is slow, right? And this brings us again to the idea we could make this much more resilient by basically just introducing a stream. And if a lot of requests come into microservice A, we just forward the event again, and then we are basically done. I mean, we're not done like we have been done before, but we say, hey, yeah, we accepted your request, we work on it, come back later, ask us if we're done, right? And if there are lots of requests coming in, basically we just pile up messages in our stream. That's all we do. Yeah, super simple. Doesn't matter how many, we just put them in a stream. And microservice B starts to take them, and whenever he's finished with one message, he just sends back, hey, I finished one of your requests. Here's the result, here's the event, and basically then just responds to the user and says, hey, we're done now with whatever you requested from us. And that's the idea. That's all the reactive manifesto. It's not magic. It's basically super low level and super simple, right? Go message driven and you get elastic and resilient system, which leads to a responsive system. Because for two things, we support queuing up of messages. That's what I just showed you. And what I showed you before, basically we support location transparency. These are the two main ideas of the reactive manifesto. And so what we do then is we move from a synchronous pull-based architecture to a asynchronous push-based architecture. And again, let's show it by examples. Yeah, makes it, I guess, a lot much easier. This big statement here, but still important. We move from synchronous pull-based to asynchronous push-based architectures. Okay, And I mentioned before, I work in the industry now for quite a while, and I did a lot of big enterprise systems. And yeah, I kind of joined the microservice journey from the very first, from the very early beginnings, I would say. And when we basically built microservice architectures in the early days, so to say, they usually look like this, right? We had a couple of microservices. Of course, it usually were much more, but doesn't really matter. And then we had kind of a web application. This web application was talking to microservice E. Microservice A said, okay, cool. Thanks for the request. I don't know what to do with it. I need to go first to microservice B. Microservice B needs to go to microservice C. And then we get back this, whole response chain. And this was kind of the first generation. And the problem is, if we do this right, and if microservice C has high latency for whatever reason, right, then our whole system starts to get slow. That's usually how we did it, right? Doesn't sound that good anymore these days. But this was the first generation of microservices. We integrated synchronously and didn't have back pressure support, right? So we just continued firing new requests if we don't get a request, and this made microservice C then usually even slower. And we then tried to isolate those high latency services with queues. These were the big times, of technologies like RabbitMQ and IMQB, right? So we kind of moved not directly from microservice B to microservice C, but we isolated it with a queue. And basically, if microservice C then was slow, the answer was slow, but it didn't in fact affect our whole system because we kind of moved into an asynchronous way of integration. And yeah, this was then the second generation, so to say, partially asynchronous and support of queuing and back pressure. And this was the time when, yeah, as I mentioned before, mainly RabbitMQ, ActiveMQ, all these classical queuing tools were used. And what we then realized, right, when we started to isolate the bottleneck, another thing in our architecture became the bottleneck, right? And so we started to put a queue there, and then we started to put a queue there, and ultimately we ended up in having everything integrated via queue. And we said, okay, if all our services are now talking to each other via queues, well, maybe we should make this as a central idea of our architecture, right? And this is usually what then happened. We had a web application that was talking to kind of a microservice, a backend for frontend or facade, whatever it is then in detail, right? And this microservice, or just a gateway, this microservice then kind of goes to stream. And that's the center of the architecture, so to say, because all requests are published to a stream. And when a user wants to create a new account, sends an event to stream, kind of microservice E is maybe receiving these events and handling them and sending back another event. And microservice B is then consuming this event, sending back another event, and microservice C is then consuming this event and sending back another event. So in the context of, as I said, a user registration, microservice E could, for example, be a compliance check, right? So we get a new event, say, hey, there is a new user registration request event. Microservice E checks it, says, okay, that looks good. Guy looks reliable. Let's send another event back that the user can be created. And then Microservice B, maybe the user service consumes this event, says, okay, I created the user now, send back an event user created, right? Microservice C is maybe the email notification service, right? Subscribes to this event, says, okay, cool, I will send out an email, and basically the whole customer journey is done, right? This was then kind of the third generation, which we saw moving to stream-centric and fully asynchronous microservices, right? And this is the time when tools like Kafka and Pulsar became very popular. And well, that leads us to the effect, basically, where we realized, oh yeah, we have now the central stream. Basically, all we do in our system is sending events and subscribing to events and reacting to events. And this, of course, leads to the effect that we say, okay, events as the system state. Events could be an interesting central system state of our system, right? And in a context of banking, for example, I mean, this is very, very, very typical, right? It's very simple. If you have a stream of transaction, let's say Max sent Tim €100, Max sent Maria €70, and Tim sent Maria €25, then based off this, of course, you could project your current balances, right? And in the first example, as I said, Max sent Tim €100. Max would then basically have minus €100. Tim would have €100. If we do the next transaction, basically Max will decrease its balance to minus 170 euros, and Maria will have 70 euros. And then, you get the point, right? And this was basically the idea. And the idea is very simple, and it's basically used or called event sourcing. And the advantage is, of course, if we go with this kind of event-centric architecture, it of course makes sense to think about if we don't want to reflect our whole system in kind of events as the state of the system. And we have this stream table duality, which is very important in this aspect, right? Where we say we can basically always go into both directions. Yeah, we could also go from a table to a stream, which is usually not so well known. But let's assume we do this a lot these days. If you have legacy databases, right? And if you want to also provide from this legacy databases events, maybe there's a legacy system where somebody writes into this legacy database all the time, and you cannot extend the legacy system, then this database usually has a DB log, which basically is just, a list of all transactions that are happening, right? And we could, for example, easily change data capture here events into our stream. So it's also working the other way around, which is quite important to know. This is, for example, where StreamSets or Kafka Connect come into play. Yeah. And this is then the idea where we said, okay, if we have all this stuff, right? If we have this stream-centric and fully asynchronous architecture, why don't we, as I mentioned before, not really move the central state into our stream, right? And this was then, so to say, the fourth or the last generation, where we said, okay, this makes sense. There we can use, for example, tools like Event Store, which basically support us in building an event store, which is really an event stream, which is also the central persistence of the architecture. And then basically we just run into asynchronous into stateless services like lambdas, which basically just take an event and produce another one, right? But it doesn't really matter that much. Yeah, that's a detail if you go into event sourcing or if you stay with classical microservices. And of course, it's also a mixture. Yeah, it's not that we build a full event stored system or we build a full non-event stored system. Usually it depends on the use cases then within your system, right? But as I said, it doesn't really matter. The important part, especially if you build microservices, is that stream-centric systems are the only way to build autonomous microservices, right? And I know that's a bold statement, but I think that's reality, and I think that's something we realized. And let me try to explain this to you why I think this way. That we need to have a stream-centric system if we want to build autonomous microservices. Well, as I showed you before, this is usually how our microservices look like, right? In the early beginnings. And to give this a little bit more drive, this example, let's give it a real domain. So we have a web banking application which has an account summary service, which has a transaction service, and which has a user service. And obviously the account summary service needs, I guess, directly talks to the user service. Then we maybe have a categorization service. This is the one that categorizes our transactions. Says, hey, this is a e-commerce transaction. This is basically your loan, and this is whatever it is, right? And then we have maybe a config service, whatever. We have a lot of services, and they start to get more. And if you work in a bank domain, usually you always need to access transactions from everywhere, right? So this leads to high pressure on the transaction service, and usually then leads to low resilience of the whole system, because if the transaction service is based on the high load, maybe not so responsive, this is a resilience effect on the whole architecture. And then maybe we have a payment service even, and the payment service is again used by web banking to do new payments, right? Not just show your current payments and your current balance, but interact with new payments. And this again has a dependency on the transaction service and on the user service, and another, right? You get the point, right? And this is what we tend to call the entity service anti-pattern, because this is what we did, right? We basically took the database tables and we kind of applied them to our microservices. And this is how then our microservice looked like. And then, we had a distributed big ball of mud. Everything was talking to everything, and it was a big mess, And then people say, this cannot be the solution. Entity service anti-pattern doesn't really make sense. We kind of want to slice our application more based on customer journeys, right? So this was the big thing then. So saying, hey, we build based on teams, build different customer journeys. So we have here, as I mentioned before, the payment customer journey, which is basically a user can trigger a payment, right? That's a good vertical for a whole team, which just deals with this problem of making payments good and fast, right? And then maybe we have this account overview customer journey. So that's the journey where the user just wants to see his current balance, his current transactions, right? And that's what maybe spawn over this architecture like this. And you see there's already a lot of sharing, right? So transaction service, user service, who owns it now, which customer journey. And the reality is even that this is much heavier. So config service, I guess, is also used by both of them. And so we have not really a possibility in this entity service anti-pattern to slice independent autonomous customer journeys into our microservice architecture. And this then basically leads to a lot of disadvantages like low service autonomy, as I mentioned before, weaker dependent deployability. So it's hard to independently deploy a transaction service because, well, it's owned usually by multiple customer journeys, right? And weak independent scalability. So we realized this very fast. I think in 2016, 15, 17, people realized it's not clever to build microservice architectures based on entities, and it's also not clever to kind of synchronously integrate all this stuff together. And then, I mean, how to solve this issue? Well, yeah, you see the pattern in this in this presentation, and please always keep in mind that if people like me are presenting something at conferences, this of course super simplified and distilled, right? I don't say that this always so like this, but in many situations we found out, or at least worked for us, if we go with an reactive event-based integration, then this could solve this problem. Because in this case, config service, whenever config is changing, it's just publishing an event. When a user service sees, hey, a user was changed, it publishes an event. When a new transaction was happening, it publishes an event. And maybe this transaction event is interesting already for the category service. So we just take this event, say, okay, let's categorize this transaction and push back another event, which is basically then a categorized transaction, right? And the next question is then what would happen if the account summary journey basically wants to see the current balance or see, I don't know, the latest 3 transactions? Would it go then directly to transaction service? No, of course not. That's the big thing here now. That's what we want to avoid, this red error, this upstream dependency. We want to get rid of this. We want to go for downstream dependencies. And we want to say, hey, the transaction service doesn't need to know that the account summary journey is interested in transactions. What we usually do is we just say, hey, we subscribe as an account summary journey to those transaction events and put them into our local projection. Okay, and that's a very important concept of projecting data, kind of read models. So what is a projection? A projection is a read model optimized for consumption and fast reads. And that's important to understand. We store in this projection here the data like we need it, right? We can store here transactions, maybe even user information, but we don't store denormalized, super clean data entity there. We store maybe from a transaction 4 of 25 fields because we just need these 4 fields for our payment customer journey. So we really try to collocate all the data which we need at this service into this projection. And we do this all the time then, right? We say, okay, sounds good, payment journey, kind of done. Account summary journey, again, we need to then project into these projections, right? And we take all the data which we need to fulfill this customer journey without having at runtime or at request time, basically, an upstream dependency. So we never write to projections. So when a new payment gets triggered, we never go directly and write to them, but we always go up to event stream and say, hey, let's assume this is a new payment event. It gets published to the event stream, and then basically it's picked up by the transaction service. It stores this information, says, hey, cool, got your payment, stored in my database, sends back an event that the payment was successful, and whoever then consumes this basically just stores it in its projection a new payment which was happening and saves it there. And when a new request comes, it just reads the data again from the projection. And that's basically CQS in a nutshell, what I just explained to you, right? And if you want to do this end to end, basically you just do the integration from web banking to the account summary, not via HTTP or REST. You use something like WebSockets, right? And you really push down to the user that a new payment was happening, and you have this this wonderful real-time experience, right? And GraphQL, for example, with subscription is a perfect way to do this. And this leads to the fact that we have now strong service autonomy at runtime, right? So services can be very independent at runtime. If the transaction service doesn't work, it doesn't affect us too much, at least if it doesn't work for, I don't know, a few seconds, because we have all the data we need in our projection. Of course, we have eventual consistency, and maybe we don't have the latest transactions there, but we have a good and usually quite real-time near projection there, which fulfills usually the customer needs and makes our system very available, where we've been before, response available, right? We have a smaller deployment footprint, so we can really deploy customer journeys without too much overlapping dependencies. And we have a good horizontal scalability. If you want to spin up a new account summary service, because maybe so many people are currently watching the account summary, we spin it up, we build up the projection during spinning it up, and we have a new instance there, right? So more or less endless horizontally scalable. Yeah? And again, what we did is nothing else than moving from a pull-based to a push-based architecture. That's the whole talk about. Yeah, it doesn't matter if you go from reactive programming or if you talk about reactive architecture. It's always this shift. Yeah, not pulling for data, but getting data pushed. And in the last few minutes, I would like to show you a few examples from our daily business to give you a little bit of understanding where we use these architectures and why we are usually so successful with them, and why our customers are also very happy with our work there. And for example, one example is insurance calculation, right? Back when the pandemic started, especially insurance companies had a big issue because it's a very personal business, right? Usually your insurance agent knows you and he talks to you and says, hey, cool, I hear you have a new car. They also need insurance for this. And, during pandemic and during the minimization of social interactions, this has, of course, a big impact on the insurance business itself, right? And so Austrian company came to us and asked, hey, we would like to make better customer experience for our users if we cannot sit face to face by them in our office or in at our agencies. And so the insurance agent, sits in front of his PC, maybe starts a Zoom call with somebody, opens up a web browser and says, hey, cool, new car. What's the brand about? Yeah. What's the build year? What's the car model? I'm not into cars at all, so don't blame me if something is strange here. But basically, this then was implemented in a very reactive architecture. So we kind of just pushed a mutation or a post to a GraphQL endpoint, stored in an event store. So whenever the user took here something, a car brand or a build year, it was published and to the various services. They kind of put the results in the event store. And the customer then had a different channel, had a mobile and tablet optimized UI, again integrated via GraphQL. And whenever now the clerk changes something, says, hey, okay, Alfa Romeo and I don't know, 2020 Giulia 110 PS. What's basically happening is very simple. We send an event through our whole system, right? The event gets automatically subscribed on the other side via GraphQL subscription, and then basically directly appears on the customer of this agency. Even if those people are not sitting next to each other, it feels very realistic. It feels very real time, right? And then the customer can click directly and say, it's correct, cool, looks good. Again, event goes back in this whole journey. GraphQL subscription on the insurance agent gets triggered. And without doing anything, the insurance agent gets forwarded to the next page. Again, we can set here the coverage. Yeah, we can increase it, or we can initially set it. Then, you see the customer sees it directly. If the clerk would move up the coverage, then of course the rate would increase, and this would have a direct impact on the user. So he will always see when he says, it's a little bit too high, can we decrease the coverage a little bit? And you don't need to explain by phone, okay, if we decrease the coverage, it will be now 200, if we increase it with 250. So it's really simple, for the user to see in real time what's happening, right? Especially in this COVID pandemic, and especially in banking and insurance industry, I had the feeling that customers expect real-time synchronization between channels quite often these days. So real-time integration is a super, super cool thing with reactive architectures, because basically you don't need to do anything, right? I mean, yeah, of course you need to still program it in a way, but the architecture gives you this property for free, more or less, right? Because you always get pushed events, whatever is interested for you or interesting for you. So that's of course a big advantage if you strive for real-time integration. Reactive architecture, I think, usually the way to go. And another example is high available banking. As I mentioned before, I have a big history, so to say, in banking industry. So I've worked in really various banks in Europe. And for banks, it's always important to be highly available, right? And a few years, I think it's 6 or 7 years back, we did a research before we started mobile banking experience, and we basically found out that what 93% of all mobile banking users do is showing current balance and last transactions, right? So maybe this, you can see yourself in this. Usually you open the app, see okay, what's my current balance, what happened the last 3 days, and then you close it again. So 93% is just about, hey, give me the latest balance and give me my current transactions, right? And then 3% is in new payments, so very small in comparison to just show me what I currently have on my account, and the rest is then other functionality like locking your card, talking to support or something like this. So if you take these numbers, you of course need to ensure that the customer is always able to see his balance and his latest transaction, whatever is happening, right? He needs to be able to see this, because that's important for the user. And if you build, again, a very simplified, of course, but similar system, right, where you have, a reactive push-based architecture, and basically you have your transactions, your users' accounts, and all events are pushed on a stream. So for web banking, for example, if you are interested in transactions, right, you start to store these transactions in your channel-specific projection, right? So as I mentioned before, projection is nothing else than a read model for a specific client in this case, right? So transactions usually had about 60 to 100 fields. For web banking, maybe 5 or 6 fields are relevant, right? So we just store the transaction with these 6 fields, very optimized for reading. So we subscribe to events and hydrate our projection, right? So we go to the stream whenever a transaction is happening. Our backend for front end here for web banking takes it, puts it in a projection. And then the client only reads from this projection. Never goes directly to transaction service. It just asks the projection, hey, what are the latest transactions, right? And if we then have, as usually in banking, a second channel, right? So sorry, it was too fast. What we often use here, for example, is a super cool technique. Basically, it's GraphQL with a Postgres database, but you can use everything for building up these projections. You can use Elastic for especially very big data, which you need to do a lot of search on. You can use Redis. You can use lots of different databases who are very valuable in this context. But you can also use them just in memory for small data, right? You don't even need to persist them in many cases. Works fine. Or use something like Kafka Streams with RocksDB or in memory state stores. Lots of possibilities to implement this then in reality, but the concept always stays the same. We co-locate the data to our consumers. And if you wouldn't have a second channel, right, like a mobile client, as I mentioned before, right, then we would have again GraphQL backend for front end with again a dedicated projection. We again store transactions. Maybe we store even less fields because we don't need that many as we would need on the web banking screen. And so we have very independent components in our system architecture. And that's important because when it comes to resilience, right, if this whole system burns down, right, if the whole back channel is not working anymore, we can still show the balance at the latest transaction to 93% of our customers, right? Maybe they cannot execute payments, right? But we can say to them, hey, restore your payments, we will execute it as soon as we're possible. So with concept like optimistic UIs, it's even, you can even increase, I think, this 93%. But it's still a massive achievement which we have, right? And we don't, right? We don't have this one of these two big problems in software engineering left. We just need to take care about naming, because cache and relation in an push-based asynchronous system is not a problem anymore. Yeah? Because we don't need to validate when a transaction or when a balance is not valid anymore, because we anyway always get pushed it, right? So cache invalidation is usually a thing you don't need to deal here anymore with when you go with reactive architecture. Okay, guys, let's sum up what we've seen. Yeah, we've seen a lot of lousy memes. We've seen lousy memes in lousy memes. I tried to explain you a little bit what the basic concept. What is a stream? Very simple. Yeah. What is the reactive manifesto? Why we need to think in streams if we want to build autonomous microservices? That we basically are just moving from a pull-based to a push-based architecture, and this usually brings us high resilience and scalability. And as always, yeah, usually all the presentations end very similar. This stuff is cool, but architecture styles always buy you options, right? So reactive architectures buy you resilience, real-time capabilities, elasticity, and extendability, right? But the important part here is they buy you those options. Yeah. You don't get them for free, and you usually pay with complexity. And in this case of reactive architectures, of course, there's a lot of complexity we didn't talk about now in this presentation, like eventual consistency or perpetual consistency. Yeah, there's a big issues you usually have to deal with, and you have to find solutions for. So as usual, yeah, as always, maybe start small and shift to reactive systems once needed. Yeah, that's it. That's my final conclusion on this. Hope it was useful. Yeah, you can reach out for me afterwards. I think we also have a short Q&A. You find the slides online. Whenever you need something, feel free to reach out via email or Twitter. One last thing, we do a free community training, especially on this topic which I talked about today. So on reactive architectures, we really do this stuff here then. So we build a reactive architecture together, and we dive deeper into the concepts of CQRS, projections, and event sourcing, which I explained to you today. So it's remote these days. We have a lockdown now in Vienna again, so it's also easily to join all over the world. Just follow the link and you will find the rest. So yeah, that's it from my side. Thanks a lot, guys, for taking your time.
Thank you, David. Thank you for some funny cats after so serious deep dive speech. I want to invite you to our discussion room. Maybe our participants have some questions and you can continue the discussion. Thanks.
Cool. Sure. See you.